By the end of the class, we're going to be able to determine the intervals where a polynomial or a rational function is increasing or decreasing. So there are some rules about that that derivatives can help us to figure. I'm going to go a little bit further than that because if we have some time, I'm going to be trying out some exercises from the University of Waterloo website, and that involves looking at something called critical numbers. So although that's the class for next week, I may just mention a little bit of that so that we can actually answer those questions. All right? Okay, let's get into it. We said that the function is increasing on an interval, and to be honest, all of what you're seeing here can be understood more easily by just simply saying that the function is increasing when it's going up. I'll be honest with you. But let me just read what it says here. It's increasing for any x1 being less than x2 on the interval where the f of x1, which means the y value, is less than the y2 value. So if you compare the x1 to the x2 value, and you compare the y1 to the y2 value, if the x1 is less than the x2, then the y2 is less than the y1 is less than the y2. Big deal. All that's saying is that the function is going up as you go from left to right. It says it right there under all that complicated looking stuff. Well, what do you notice about the slopes of the tangent? The slopes are all positive, right? So if the function is increasing, and that's something we even talked about, thank you, Stephen, right? That's something we did talk about when we were doing a question from the previous unit, that if the slope, excuse me, if the slope is positive, it means the function is increasing. Just give me 1 second, please. Sorry. When the function is decreasing, if you're comparing the x1 to the x2, then the x1, as for decreasing slope, if one is less than the other one is greater than the other. If you compare the x's, if you compare the y's, if this is less than this, then this is greater than that. Or in other words, the function is going down as you go from left to right. Right? That's the easier way to look at it. And this sort of complicated language probably doesn't help anybody, but that's the way it's set out in the textbook, so I thought I'd just repeat it here. What do you notice about the slope? Slopes are negative, right? So that's the important part of the observation. Slopes are positive here, right? If I put an IROC or a tangent line right next to this function, it would give me a positive slope. If I do an IROC between these 2 points here, or just put a tangent line across there, that would be a negative slope. All right, so it's pretty simple rule. So the rule is that intervals where the function is increasing and or decreasing, we simply look at the derivative. Derivative is negative, it's decreasing. Derivative is positive, it's increasing. All right? Simple rule to follow. So here is, and let me just sort of make sure we are clear on that. We're looking at not whether the derivative is going up or down, but whether the derivative is positive or negative. That is it. A positive derivative means the function for that section is going up, period. A negative derivative means the function for that section is going down, period. Okay? So find the intervals where this function is increasing. Without drawing it, can we figure out where the function is increasing? Of course we can. So what we're going to do is we're going to go ahead and find the derivative of the function, right? And we know how derivatives work already. F prime of x is going to be equal to x squared plus 4x minus 12, right? We've been deriving functions now for a while, so we know how this works. 3 times 1 over 3 is 1. Take 1 from the exponent, so it's just x squared, and so on and so forth. This function, if I want to know where the function is increasing, I need to know where this thing is positive. So I need to figure out where's x squared plus 4x, x squared plus 4x minus 12 greater than 0. Not where it's equal to 0. Many times when we're doing this, we wanted to figure out where there was a horizontal tangent. Now we want to know where the thing is not equal to 0, but where it's greater than 0, because we're trying to figure out where this is positive. Well, remember how we did this. How do we know when this function, it's a quadratic function, folks, right? Regular garden variety quadratic function. How can I figure out where this thing is positive? That's what being greater than 0 obviously means. Remind me how I can figure out where this is positive. Without running to Desmos or anything else, tell me how I know where this is positive. What's the best way to do it? Find the zeros. Okay. And first to find the zeros, Stephen and Adam, right? Let's first of all find the zeros and leading coefficient. Yeah, but why don't we just factor this first? First to find zeros, we need to factor it. Really? That's the most important thing. All right. So I agree with both of you, but let's factor it. So I'm going to say, well, what are the factors in this case? Well, x squared plus 4x minus 12. 6 and minus 2. So x plus 6 and x minus 2. So yeah, we do need to find the zeros, and we factored it so we could find the zeros and try and find out where this is greater than 0. And what have I always said is the best way for us to use that information now to figure out where it is greater than 0. Where do we go next? We sketch. Thank you. Thank you, Adam. We sketch it, right? This whole unit is about sketching curves. And I'm going to be honest with you, right? This is where teaching this remotely has a big disadvantage, and that is that I am going to have to depend on you to not simply run over to Desmos to get answers for these questions, because curve sketching is about knowing what's going on with the curve, not because Desmos says that this is what the curve looks like, but because we have this information in the equation and we can relate that information to what's going on in the function, and therefore we can sketch it. And there's no way of me monitoring that from afar, so I'm going to have to depend on you to be honest about it. All right? So, our number line, yeah. So, I'm going to go ahead and put the two zeros that both Steve and Adam talked about before. So those zeros are at minus 6 and 2. So minus 6 is over here, and 2 is over here. That's obviously not drawn to scale, clearly not drawn to scale. So I'm going to go ahead and draw a sketch of the function through those lines. And again, that doesn't look quadratic, so please just, cut me some slack here. And if I draw it like that, it's now easy for me to answer the question. Where is this thing increasing? Where is this positive? From where? What intervals are positive on this graph? Give me the first interval, please. Anybody, right? So minus infinity to minus 6. Good. Minus infinity to minus 6. Do I put a square or a round on that? What do you think, folks? Square or round? On the same. Well, we know infinity. I see Adam has put round on both ends. Why not put a square on the minus 6? What would be wrong with... Why don't I consider... And by the way, you're right. Why don't I put a square on the minus 6? Is there a good reason why I wouldn't consider minus 6 to be part of my answer? Right? Doesn't include minus 6. Why not? It's greater than, not equal to. It's not equal to. Well, what's happening at 0? Is it not increasing at 0? What's happening at the 0? Right? When the derivative is 0, what do we know about the function? What's happening at that point? What's the slope at that point? Right? The slope means what's happening at that point. Horizontal slope, which means that it's neither increasing nor decreasing at that point. Right? It's just turning. So it's neither increasing nor, so it's probably that point where you have either a max or a min. It doesn't have to be a max or a min. We'll talk about some of that later on. But it's not increasing at a max or a min. Right? That's not a point where it's increasing. It might be increasing just before that or just after that, but it's not increasing at the point where you have that horizontal tangent. So we don't include the minus 6. And the other part where it's greater than 0, of course, I can see that that answer is already in the chat somewhere. I think somebody had that answer before. I think somebody had that answer before. Or maybe not. Maybe not. Maybe not. Oh, yeah, see, Sarah had that answer before. From 2 to infinity. All right, and again, round brackets on both sides. This is a fairly easy question to answer. Right? If I drew this and I don't have the actual draw, I wonder if the thing will draw this for us with f of x. Can I do that? Math actions, yeah, no, it doesn't. And you know what? I'll just leave it as this. But anyway, if you drew this, if you did go ahead and draw it, you would see that the function is increasing between minus infinity and minus 6, and then from 2 to infinity. All right, I don't have a picture of that, You can try that out yourself. And it's a union. Yes, thank you, Richard. It's definitely a union between those two things. All right. Okay. Nice, easy one to start us off. Next question. Find the intervals where this one is decreasing. So the first one was increasing. This one is decreasing. So we do the same thing again. Excuse me. We have to find the f prime of x, and that's equal to x cubed. You're supposed to be express at this by now. Minus 3x squared minus 4x plus 12. That is my derivative. Okay, this isn't a quadratic though. So how do we do this one? Right? Can you help me to figure out how we would figure out where? So what I'm asking is, where is x cubed minus 3x squared minus 4x plus 12? Where is that not greater than but less than 0? Right? Can you walk me through the process? If this was a question on a test, and again, you're not using Desmos, right? How do I proceed from here? Factor by grouping. Why would you think, Richard, that we could factor by grouping? How do you know that we could factor by grouping? Is there some little trick that somebody might have taught you, maybe Mr. Kamukt or somebody that tells you that you could factor by grouping? Okay, so Adam is right. If you see what Adam has there, and Richard probably has the same idea. You multiply the first number, which is the 1, by the 12, right? I'll circle both of these things. The 1 is implied. And if you multiply those two things and get the same thing as these two numbers here, then you know it can be factored by grouping. Absolutely, Adam. Absolutely, Richard. So let's go ahead and do that. The common factor between the first two terms is, help me out, folks. What's the common factor between the x cubed and the minus 3x squared? What's that common factor between them both? Don't let me have to bring the wheel out now, folks. X squared. Thank you very much. So x squared, I'm going to have x minus 3 there. And what's the common factor between the next two terms? The minus 4. Good. So minus 4 into x minus 3 less than 0. Okay, so I'm looking at that and thinking, okay, I have x squared minus 4 in one, x minus 3 in the other, less than 0. This, of course, factors into x plus and minus 2. And I'm ready to draw my graph, right? That shouldn't be too difficult to draw at all. So I have a plus and a minus 2 here. And I have a 3 as well. Because those are the zeros that came out of that bracket, of those brackets. And if this is a cubic function with a positive lead coefficient, think back to your advanced functions class. It should start off in quadrant 3 and end up in quadrant 1. It should look something like that. Okay? Again, all I'm really interested in, though, is where is this function negative? And this function is a derivative of my original quartic function. The quartic function was this. This is my cubic function derivative of the original quartic function. But the answer is still based on where is this negative? I'm looking for where it's decreasing. Where is this thing negative? So since I'm only hearing from Adam and Ashwin and a few, oh, okay, I got so okay, all right. So look at that. I'm getting answers from Stephen and Elish and Fernando. I'm going to see if they're both saying the same thing. They both seem to be saying the same thing, and I'm going to agree with them both. Right? I'm going to say that this thing is going to be negative, which means that the function, the original function was decreasing anywhere from minus infinity up to minus 2, union with 2 to 3. Okay? All past Alexander says again. Okay, Alexander. Remember, you have 5 minutes. It's now 1:56. All right. So that wasn't too hard at all. A and B were fairly straightforward. As long as you can differentiate, as long as you can factor, you're good to go. Problem C takes it up a notch though. Now we're looking at a rational function. Still asking where's decreasing, but it's a rational function. And let's take this and do what we know we have to do with it in terms of derivative. Okay, so dy dx. So dy dx of this, remember, the derivative of the top, which would be 6x, multiplied by the derivative of the bottom, x squared plus 9, minus the derivative of the bottom, which is 2x, multiplied by the underived top, so 3x squared plus 4. You are all supposed to be pros at this by now. All divided by x squared plus 9 squared. Okay, let me just double check that. I make mistakes sometimes, so I just want to make sure I didn't make any mistakes on this one. The root of the top is 6x times the underived bottom, x squared plus 9 minus 2x times 3x squared plus 4. Okay, great. All right. Where do you think I need to go next? Well, I think we all know that we should try to expand the top and simplify it a little bit. So let's do that. So I'm getting 6x cubed plus, what is that? 96 is 54x minus 6x cubed minus 8x all over x squared plus 9 squared. Okay, so I'm thinking the top of this 54, okay, the 6x cubed and the minus 6x, this is 6x cubed. Before anybody points it out, I realize that it is in fact cubed. The 6x cubed and the minus 6x cubed do seem to cancel each other out, so that's good. So that leaves me with a regular linear function, which looks like it should be 46x, I'm going to say. 46, 54. No, that's not right. 8 from that is 40. 54 minus 8 is 56. Oh, 46. Is 46 right? Yeah, 46 is right. Yeah, okay. I don't know why I was doubting myself there. Over x squared plus 9 squared. So we're asking for where this is decreasing. So where's this less than 0? That's the question. Thank you. Thank you, Tomaleo. Thank you, Sarah, by the way. Excuse me. So, how do we answer that? All right, I need some thoughts on that from the class. All right, this is a rational function now, right? And it has on the top 46x and on the bottom x squared plus 9 squared. Find the asymptotes. You're thinking we should sketch it, Stephen? Is that where you think we should be going with this? And somebody, okay, Sarah's saying something with the numerator. Could we use a table, Taj is thinking? We could do all of those things, but I'm going to point something out to you. We can tell whether this thing is positive or negative by just looking at the numerator. I'll tell you why. And I think it was Sarah who said that earlier on. The bottom of this function is something squared. If that is true, and Sarah just said it a while ago, the bottom of this function is always positive. Isn't that true? In fact, it can't even be 0. It's just not even possible to be 0. The bottom is always positive, right? Because any number you put into this thing, after you square it, it's going to become positive. And in fact, beyond that, it's x squared plus 9, which means that the smallest value that you could have in that denominator is actually 9. If x was 0, it would be 0 squared plus 9, which would be squared itself, which is positive. So all I'm saying to you is this, and Sarah seems to be on the same wavelength with this. Since the bottom of this function is always positive, the only time that this function can be negative is if the top is negative. right? So we should be focusing on the top, the 46x, right? When that is negative, the whole thing is negative because the bottom is always positive. I want to make sure that the logic of what I just said is clear, okay? Anika, what do you think? Does that make sense to you, what I just said? Okay. So where is 46x? What value of our values, it could be more than one, what kind of values of x would make, not just Anika, by the way, so I'm not targeting anybody right now, what would make the numerator negative? We want it to be less than 0. When x is less than 0 is absolutely correct. So just make the x negative, the whole top becomes negative, right? Any value of x that makes it apart, so not 0, but any negative value of x will make this numerator become negative. And if the top is negative, we already said that doesn't matter what the value of x is for the bottom is always positive, right? That means that negative top, positive bottom makes this fraction negative. And 46x, and let me just sort of make sure we understand why that is, right? I'll just draw a quick little diagram here on the side. The 46x is a function that goes through the origin, because there's no x-intercept there. This goes through the origin and has a slope of 46, very steep line. Anything to the right of 0 is positive, it's above the x-axis. Anything to the left of 0 is below the x-axis, it's negative. So this is negative when x is less than 0, right? Soon as x is next to less than, or another way we can write that is anything from minus infinity to 0. But not 0 itself. 0 is not included. All right, thanks. So Stephen, thanks. Does that make sense there? So if I were to draw this thing, draw the original function, it would be decreasing anywhere to the left of 0, right? But apart from that, it would be increasing. Okay, hopefully that made sense to everybody. I'm going to move along. Now, look at this graph. This is the graph of the derivative function. Not the graph of the function, it's the graph of the derivative function. Give a possible sketch. So we're not necessarily going to give you the actual graph of the original function, but at least some notion of what it might look like. Assume that the f of 0 is 1. So they give us some more information. So there's one point that we know on the original function is at 0, the function is at 1. So I'll put that in as a red dot right here. F of 0 is 1. That's one point that's on the line. So what can we tell from this derivative? We can tell that it looks like this line is positive all the way from minus, it's a straight line, anywhere from minus infinity all the way up to 4. Then after 4, it becomes negative. All right, so that's what we know so far. The other thing that should strike you is that at 4, the value of the function is 0, which means that the function that we are going to try to draw should have a horizontal tangent at that point, and it suggests that that point, the original function, would be a quadratic. Yes, Taj. In fact, it would suggest a quadratic because this is a straight line, and if you took the antiderivative, and we talked about this in the last unit, of a straight line, we should probably end up with a quadratic. Okay? So anyway, so if we look at the 4, it looks like right before we had a 4, it was increasing, going up, going up, going up. Then right after the 4, it was decreasing. To me, that suggests that the 4 is actually a maximum point. We're going to talk some more about that tomorrow. That's going to come up in the thing that we're going to be doing a little later on the University of Waterloo website. That's telling me that at the 4 should probably have some kind of a max point there, right? No, is it at 4, 4? I don't know. It could be somewhere down here. I don't really know for sure, but I'm saying that something is happening at the 4. Let me take off the last one there, which would suggest that it has a horizontal tangent. So I'm thinking, okay, this function is probably, and I don't know any other points on the line, right? I just know that the line probably looks something like this, and then starts to come down after that, right? How do I know that it's decreasing after 4? Because the derivative went negative, where I'm pointing to right now is below the line, below the x-axis. That's a negative value, and it means the function is decreasing after that. And the function before that, excuse me, is positive. This whole line here is positive. Everything from 4 to the left is positive. So the function was increasing. It told us it went through this point at 0, 1, by the way. So I'm actually making the point go through there. The other thing that should be the original for, what about what's happening tomorrow? What are you talking about here, Adam? I'm a little confused here. I said tomorrow. I said tomorrow about what? That we're covering something to. If I said tomorrow, that must be it's Friday, so it can't be tomorrow. Okay. Yeah. I'm not calling it to come to class tomorrow. No, that's not what I'm not doing that. Okay. I meant next week. Sorry. Yeah, no, there's no classes scheduled for tomorrow. We all need that weekend. Sorry about that, Adam. Anyway, so one of the things that will come up in the thing that we're going to be doing on the University of Waterloo website is that we can actually tell a little bit more about this point at 4, because if the slope of the graph was positive before it, and you can see from where I'm pointing to right now is positive here, then it goes negative afterwards, it would suggest that we have a maximum point, right? Fernando, yeah, no, not at all. We have a maximum point here. So when you go from positive to negative, positive means you're going up, negative means you're going down, right? That would mean that you have a maximum point at that 4. So that's what it suggests, right? That's exactly what it suggests, and that's why now it says a possible sketch, because I don't have every single point nailed down, but I know that at 4 it looks like I have a maximum point right there. And it has a horizontal tangent. So if I put a tangent on the graph right here, right, just touching it, that has a 0 slope, and that corresponds to this 0 on the graph, which is supposed to represent the derivative of this red line. Okay? All right, so there's a possible sketch with f of 0 being 1. All right, so there's one point we know, and we know that at 4 we have this maximum point where the graph is turning from being a positive slope to being a negative slope. And this is the slope line. It went from positive, it went to negative. Something else I should point out is that this line is getting a smaller and smaller value of y. So the y values are dropping as we go this way. That's consistent with this line, because think about the slope of the line right at the beginning. That's a pretty steep slope. And as you move along the edge of the curve, you notice that the slope is actually flattening out. Right? And that tells me that I have a decreasing slope. We were talking for my class, if you had me in advanced functions, I talked about when that tangent line is rotating clockwise or counterclockwise. This particular tangent is actually rotating in a clockwise fashion. So it's steep here, it's flatter, flatter, flatter till it gets really flat here. It continues actually rotating up in a clockwise manner, and you can see that this derivative function continues going down. It keeps going down, 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 down. So this decreasing slope will actually continue because this line is decreasing, and that's why that rotation would continue to be a clockwise rotation. Okay, hopefully that made sense. I'm going to move along from there. Next graph, next question. Given this graph of f prime of x below, graph a possible sketch. Again, we're not going to have every single point in the correct place because we don't have enough information to do that. But give a possible sketch of f of x, and again, assume that f of 0 is 1. So the one point that I do know is this point right here. Okay, Now let's think this through very carefully. Two things that I know is that this curve that I'm trying to draw has a horizontal tangent at -2 and another one at 3. Let's first of all accept that, right? I want to make sure everybody understands that. Ariana, did what I just said a while ago make sense to you? That there are two horizontal tangents. Ariana, are you there with us? Go. That there are two, okay, that there are two horizontal tangents. One is here and the other one is over here. No, I started off being negative, right? Let me point to it. It's being negative here, then it turns positive, right? So negative turning positive would suggest that I was going down first, then I started going up. So that would suggest I have a minimum point at that too. If you think about that, does that make, Ariana, just want to check in with you, does that make sense to you? If I went from a negative slope to a positive slope, it probably means I have a minimum point right there. Does that make sense, Ariana? I just want to make sure that that makes sense to you. Okay. And everybody else, let me check in with the rest of the room as well. Braden, how about you? Does that make sense? That it looks like we have a minimum point at that -2 there. Braden, does that sound about right to you? Okay. All right. And let's see now. How about Javier? Javier, does that fact that it might have a minimum point there make sense to you as well? If I go from a, thank you. So if I go from a negative slope, so negative slope means that I'm going down, right? And then I suddenly start to turn up, right? Negative to positive, which probably means I have a minimum point right there. So now I'm going to suggest maybe somewhere down here, right? That I'm going down, and then I started going up after that. I have to go through this point right here. Now, up here, right? This is suggesting, well, let's come over here first of all. Let's come over with the 3. What's happening at 3 is that it sounds like I'm going from what used to be a increasing function. So here's where I'm at 3 right now. I used to be increasing because I was positive, and then I became negative. So it sounds like I'm now decreasing after that. That's what it sounds like to me, right? So it sounds to me as if I had a minimum point over here. It sounds like I have a maximum point where I'm at 3. So I'm going to say that probably something like maybe that is happening, right? And then I'm going down after that, right? Why am I going down? Because remember, after I get to the 3, the function is below the x-axis. So it sounds like I'm going down after that, right? So I'm trying to put the 3. Okay, great. There we go. All right. So what I was trying to say before things kind of went haywire there is that at 3, it seems as if we have a point where the function is not only going from, remember, it's positive and then it's negative. So it has a positive slope and then suddenly, okay, I meant it to be red. I'm not even sure if I want to try changing colors anyway. Want it to be red, want it to be red. Okay. Okay, anyway, so it goes from, look, you all know where I'm trying to go with this. So if I don't even have it right on the 3, then you know what I'm trying to do here, right? So right there at that point, it looks as if the function has this maximum point on it, right? That's all we can really say. It's going to be interesting to talk about this point here, by the way, right? When we get some more into this kind of function. We're going to be calling that a point of inflection later on. So where this first derivative has a horizontal tangent, we're going to be using that in more detail and talking about in more detail in another class. But that's something you should sort of, pay attention to. But for right now, this red line that I've just drawn is a reasonable representation of what the original function would have looked like with a derivative like the one that I'm looking at right now. The main focus is what's happening at the -2 and what's happening at the +3. At the -2, we're going to suggest that we have a minimum point because the function went from being a negative slope to a positive slope. And at the 3, it's the opposite. It went from being a positive slope to a negative slope. So we think it has a max right there. Okay. All right. Let me see if I can continue with this. So let's look at this function, by far the most challenging one. One point they've given us is that at the f of 0, it's equal to 0. So let's put that point in. Now, notice that to the right of 0, the function, the derivative function that is positive, which means that the function actually is rising anywhere from 0 onward. To the left of 0, this derivative is negative, which means that the function should be falling on the other side of that 0 as you go from the left to the right. Now, here's the thing. This slope, right? The slope of the function is what the derivative is showing us. It's actually rising up to a point, and then the slope still is positive, but the slope is falling. So I'm thinking of a slope that might, for instance, look something like this, where it's getting steeper and steeper, and then it kind of starts to level off and do something looking like that on that side. So it's not like it is not rising, but it's just rising at a slower rate because it's leveling off. But on the other side, the function also needs to be going down. So I'm thinking it might look something maybe like this. Now, this is supposed to be symmetrical, so maybe my graph doesn't look that symmetrical. And maybe I should make this part over here look a little bit more like the function continues to go up. So it's going to be going up again, right? But again, it's slowing down in the fact that it's leveling off, but it still continues to go up. Well, I actually have the function here to show you. So it's behind this graph. I've been hiding it behind this graph here. The function that we're looking at right now is a derivative function, which is actually this function right here. So let me first of all show you the derivative on the graph. Okay, so there's my derivative function. The actual function that generated this derivative is this function right here. If you were to derive this function, you would get this function over here, which you can try in your own time. So I'm going to go ahead now and show you what this function looks like, a much better rendition of it than my crooked drawing. And there you go. So it does in fact have that kind of a V or U shape for a while, and then it kind of just flattens out towards the top. And that is what that relationship between the derivative function and the actual function has. So this is the last one that we're going to have before we get to the stuff that's on the University of Waterloo. Sketch a graph of a function that's differentiable on the interval between -3 and 5, so we have enough room to do that, and satisfies the following conditions. The local maxima are at -210, so we can just put that on the graph. -210 is somewhere around here. There's a local maxima there, and at 3, 4. Are the local maxima right about there. All right, so those are local maxima. The function is decreasing on the intervals between -2 and 1, right? And between 3 and 5. The derivative is positive, which again would suggest it's increasing between -3 and 2. And for 1 to 3, the f of 1 is -6. There's another point we can put on there. F of 1 is equal to -6. So that's somewhere about down here. Okay, so this should be fairly simple to do. The increasing interval is between -2 and, where am I? Decreasing on the interval between -2 and 1, right? So between -2 and 1, here is 1 right here, it's decreasing. Right? And then it's going to go through this point right here. And let's see now. And then from 3 to 5, also it's decreasing. So from 3 to 5, it's also decreasing. So here it's decreasing. And then it's positive. So between -3 and 2, let's say this is -3 and 2. So -3 to 2, it's increasing. So something looking like that. And then from 1 to 3, it's increasing again, so maybe it comes down here, and it's increasing again from there. F of -1 is 6. All right, so that's not a particularly challenging question. Just kind of just sort of following on what we did. The only thing is that it doesn't tell you that the function is decreasing or increasing. It just says the derivative is positive between -3 and 2. So nothing particularly spectacular there.